Hello, can you hear me? Hello. Okay. So, today I will introduce few basics of normal distribution. I know you are going to study that part parallelly also, but because you yesterday mentioned that you are yet to study it, I thought I would introduce whatever things are necessary for my part. Maybe it would be repetition, but I think it should be okay. So, first of all, you have studied binomial distribution, etc., right? You have studied binomial and perhaps geometric, and I guess even Poisson. Am I right? You have studied these three distributions. Yes. Have you studied these distributions? Yes. Have you studied binomial, geometric, Poisson, these distributions? Yes or no? Hello. Okay, you haven't. Okay. But I thought there were some questions in your question paper that I saw, some waiting for the bus, etc. So, how did you solve those questions then? There was some internal question paper posted on the WhatsApp group. Okay. So, but do you know these terms? Probability mass function and probability density function, or cumulative distribution function. Are you aware of these terms? Yes. Okay. So, all these three terms you know, right? Okay. So, there are some standard probability distributions in statistics. What do I mean by distribution? They give you spread of the data. They tell you something about the spread of the data. For example, the simplest one is what is known as Bernoulli distribution. So, there are let's say there are 30 people in your class, okay, and I introduce a random variable xi as 1 if ith person is present today, okay, if ith person, so by roll number, let's say, so the person with roll number I is present today, and 0 if the ith person is absent today, okay. So then I will have x1, x2, x30. Some of these values will be 1, some of these values will be 0. So this, so this is a classic example of Bernoulli distribution. So there are only two possible values, 1 and 0. Now suppose it is known to us that normally 70% students attend classes. Suppose this is known to us, okay. Normally 70% students attend classes, okay, or we can say other way round. Normally the chances of attendance are 70%, means what? that university expects you to attend 75% of the classes. Okay, so suppose that probability of a student attending a given class is suppose 75%. Then in such scenario I would say probability of XR, and we will assume that for every student it is same. Okay, I know this is not a valid assumption, but here we will assume that all the students are equally sincere and they have equal chances of attending any given class. Then probability of xi equal to 1, that is probability that ith person is present in the class is 0.75. Okay, so here in Bernoulli distribution we call this as probability of success. Okay, generally the event which is denoted by 1 is called as success. So here attending the class, and event which is denoted by 0 is called as failure. It has nothing to do with the actual meanings of the word success and failure. Okay, this is just terminology. So now what does it mean? It means that I can now use this probability to compute the expected number of people in the class. Okay, so expected number of people means what is the expected attendance of the class, that I can compute using this. So normally if every person has chance 75% of attending, then expected count of people who are attending the class would be 0.75 into 30, correct, 0.75 into 30. So this can actually be obtained via what is known as binomial distribution. So binomial distribution actually comes from sum of Bernoulli random variables. So for single student we said that xi we take as 1 if ith person is present, we take xi as 0 if ith person is absent. Okay. Now when I want to talk about entire class of 30 students, first I will assume that for every student probability of attending the class is same, and second assumption that we will have is whether a given person attends the class or not does not affect the chances of other student attending the classes. Okay, so you don't bunk classes together. Again, that's not a valid assumption, I know, but still we'll assume that you don't bunk classes together, and whether you are present, so if one person is present, that does not affect the chances of other person being present. Okay, so the two assumptions are Bernoulli random variables with same success probability, every student has same chances of attending the classes, and they are independent of each other. Okay, in statistics that is known as IID. Okay, the terminology in statistics is IID, means your x1, x2, x30 are independent. Okay, this first I is for independent, and this ID is for identically distributed. Okay, identically distributed means the probability of every student attending the classes is same, and independent means whether one student attends the class or not does not change the chances of other student attending the class. Okay, so in such case, now if I want total number of students present in the class, okay, total number of students present in the class. So we are anyway saying that I would take xi equal to 1 if a student is present, and I would take xi equal to 0 if a student is absent. So if I take sum over all xi's, then that would give me count of students present in the class, correct? If I take sum over xi's, then that would give me total count of students present in the class. Is it okay? Is it making sense whatever I am saying? And then we say that this distribution is binomial with 30 as, because there are 30 students, so 30, and the chances of attending as my success probability 0.75. Okay. Now what is interesting about binomial? In Bernoulli there were only two possibilities, 0, 1. In binomial now I am saying it is total number of students present in the class. So what are the possible values of this? Total number of students present in the class can be 0, it can be 1, it can be 2, and it can go up to 30, because we are saying that the class size is 30. So at most there will be 30 students present in the class. You cannot have 35 students present if the class strength itself is 30. Okay. So this upper bound is known as n, okay, or size parameter. Okay, this is known as n or size parameter in the binomial distribution, and this is again called as success probability. And how do you compute PMF of binomial? So probability of x equal to x. So out of n, so out of 30 students, what are the chances that x students are present? So that would be n choose x, because which x I don't care, so n choose x, then present, so p raised to x, and others should be absent, so 1 minus p raised to n minus x. And this is true for every x between 0, 1, 2 up to n. Is it okay? Are you following what is happening here? Yes or no?
Yes, ma'am.
So this is known as PMF of binomial distribution, because it gives me probability of each x. So suppose I want to so today how many people are present in the class? So I can see 20, so 19 people, right? Or 18 actually, 2 are me, one is presenter and one is speaker. So 18 people are present in the class today, so I can compute probability of x equal to 18 as 30 choose 18, then 0.75 raised to 18 and 0.25 raised to 12. Okay, 12 comes from 30 minus 18, okay, n minus x. I will later show you the graph of binomial distribution. So this is binomial, one of the what we call as discrete distributions. Okay, why discrete? Because it takes only integer values, 0, 1, 2, etc. So you can't say that today 19.5 students were present in the class. Okay, so discrete. Another example of discrete distribution is Poisson distribution. So what is Poisson distribution? Now in binomial I said there is an upper bound. So when I am counting something where there is a fixed upper bound, I can use binomial. But when I want to count something where there is no fixed upper bound, for example, if I want to compute what is the number of people, if I want to estimate probability of say 10 people visiting an ATM in 1 hour. Now technically number of people visiting an ATM does not have an upper bound, right? One person can visit, 10 people can visit, 100 people can visit, and in I mean in theory even values like 1000 are possible. Okay, even 1000 people may want to visit ATM in a given hour. That is possible. So there is no fixed upper bound. So in such cases we go for Poisson distribution, and generally it is used for modeling rare events. It is more used for modeling rare events. In fact, the word Poisson, of course, here it comes from name of the scientist, that's why P is capital, but it does have some meaning in French. Does anyone by chance know what is the meaning of the word Poisson? Yes, any idea? No. Okay, so this actually means fish, okay, in French. And there is a story, they say that, how do you remember that Poisson distribution is for rare events? So generally French aristocrat people used to go for fishing when they had nothing else to do. Okay, so their pastime, one of their pastime was fishing, and because they were royal people, they did not really know how to fish. So what would happen is they would spend hours and hours, and still they wouldn't get much. They wouldn't be able to catch too many fish. So for them, catching a fish was a rare event, and which is generally modeled by Poisson distribution, count of something rare. A typical example is number of typing mistakes on a single page in a book. So generally this count is going to be 0, right? Number of typing mistakes on a single page, or number of people visiting an ATM, etc. In fact, Poisson distribution has lot of applications in call center modeling. So for example, if you own a call center, you want to decide how many operators you should employ. Okay, you want to decide how many operators you should employ. Now there are two possibilities. If you hire too many operators, and if you don't have that much work for them, then you are unnecessarily spending on their salary. Okay, and you don't want to lose your money unnecessarily if you want to run a successful business. If you hire too few operators, then what would happen is your call center will receive many calls, but you won't have enough operators to handle those calls. So customers will have to wait for a very long time. That would frustrate the customers, and they may even end up giving up your service. Okay, for example, if you are a telecom company, then they may end up switching to some other network provider. Okay, so you will lose business. So either value is not acceptable, means too high count of operators is also not acceptable, too low count of operators is also not acceptable. So how do you decide optimum number of people you need to hire? So you can use Poisson distribution there. Okay, you can see how many calls are there every hour, then what is the typical duration of a call, etc., and then doing some modeling, you can reach the optimum number of operators that you need to have in order to make sure that you are not having, you are not paying salaries unnecessarily, and that customers are also getting service without too much of a wait. Okay, so Poisson distribution, as I said, is generally used for modeling rare events, and it has no upper bound. Okay, so technically it can take any values. Of course, the values become less and less common, less and less probable as you go to high values. So the PMF of Poisson distribution, probability of x equal to x, is given by e raised to minus lambda, lambda raised to x upon x factorial, where this lambda is a positive number and this is actually mean of that distribution. Okay, so mean or expected count, and x is the possible value. So x can go from 0, 1 to anything. Okay, so this is PMF, Poisson PMF. Actually, in the binomial distribution, if your n, that is the upper bound, goes to infinity and if your success probability goes to 0, then generally you reach the Poisson PMF. Okay. So, this is another important, this is again discrete distribution, because here also we are modeling counts. So, you can't have fractions. By the way, the mean can still be fractional. Okay. Mean can be fractional. For example, I can say average number of family members in an Indian family is 4.2. Average can be 4.2, okay, because you may have some families with 4 members, some families with 3 members, some families with 5 members and so on. So, average can be fractional, but the individual counts are not fractional, they are integers. So, this is another important discrete distribution, and I will introduce only one more, that is geometric distribution. Now, when do you use geometric distribution? Geometric distribution is generally used when you want to estimate something like probability of success or probability of say k number of failures, etc. Okay. So, suppose you are throwing say darts, okay, and on every throw chances of you hitting the target are, let us say, 0.7. Then what is the probability of an event that you will need at least 3 throws to get the correct to hit the target. So, you will need at least 3 trials to hit the target. So, for estimating such probabilities we use geometric distribution. Okay. So, you have some initial failures. So, you have sequence of failures F, 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 and then you hit success. Okay. So, if I want to compute probability of getting success in kth attempt for the first time, okay, probability of getting success in kth attempt for the first time means all the earlier attempts result in failure. If I want to estimate that probability, then how do I compute that? Probability of x equal to k. So, all the earlier attempts have to be failure. So, 1 minus p is the failure probability. So, 1 minus p raised to k minus 1, and then the last attempt has to be a success. Okay. And k will go from 1 to etc. Okay. Is it okay? So, geometric distribution, another example of geometric distribution is, suppose you are waiting at a bus stop and buses are coming. Of course, not every bus is going to be of use for you. So, how many buses do you have to let go before you get the correct bus? Okay. So, the bus in which you actually intend to board. So, such events where you have again success failure type of scenario and you want to model the number of failures required before the success or chances of getting success in the kth attempt. So, sometimes another form for geometric is, if you are simply modeling number of failures before the first success, if you are simply modeling number of failures before the first success, then you have another form, probability of x equal to k is p raised to 1 minus p raised to k into p, because now I am saying number of failures. So, there can be 0 failures, there can be 1 failure, there can be 2 failure and so on, and again there is no direct upper bound here. Okay. If you are very unlucky, you may have to keep trying for a very long time to get the first success. Okay. So, these 3 are known as discrete distributions. Why discrete? Because they take only integer values, they do not take fractional values. And I will now show you graphs of some of these. So, for example, binomial and Poisson, I will show you the graph, and we will see how the probabilities or the PMF changes when you change the parameters. So for binomial, the parameters are n and p, that is size and success probability. For Poisson distribution, the parameter is lambda, that is mean, and for geometric distribution, the parameter is again p, which is success probability. Okay. So let me stop sharing for a minute and can you see my screen? See, before we go into the graphs, this is one interesting question. Can a worst failure be an indicative of a great success? Okay. So there is a story which actually tells you why you need to know all these distributions. So this comes from a TV series called Numbers. It's an American TV series. So in this TV series Numbers, they have the two lead characters. One of them is a mathematics professor and the other one is an FBI agent, and they are brothers. And this FBI agent, whenever he gets some interesting case which he cannot solve using usual methods, he takes help of his mathematician brother. Okay. So this is a story from there. So there are some kidnappings going on and some girls are being kidnapped, and these FBI people are trying very hard to locate the kidnapper or the reason for kidnapping, etc. And for some reason they are unable to succeed, and his mathematician brother is also trying some sort of modeling. So they have found bodies of some girls, and then using those locations, this mathematician brother is also trying to predict a possible location of the kidnapper, etc. But they are not getting much success. Now what happens? Suddenly one person approaches FBI and he claims that I have some psychic powers, I have some extra sensory psychic abilities, and I can help you in this case. Okay. So this FBI agent is actually already frustrated because things are not going correctly. I mean, he is unable to get any good leads. So he says that okay, whatever works, I am willing to try. So he says to this psychic person, okay, so if you feel you can help us, please help us. Whereas the mathematician brother, he gets very irritated. He says, nobody has this psychic powers, etc. This is all superstition. Why are you believing in him? You shouldn't believe in him, etc. etc. And then he says that okay, if at all you want to believe in him, we should first test him. We should first examine whether he really has psychic powers or not. So he designs a very very simple test. So what is that test? He says that we will show him a series of cards, right? Playing cards. So cards are of two type, either red or black. Okay. So he says that we will show him 25 cards. Okay. And actually sorry, we won't show him the actual card. We will just hold the card in front of us, and we will ask the person to guess whether the card is red or the card is black. And out of 25, if he could guess many of them correctly, then I'll believe that the person has psychic powers. So all these people agree. They say okay, so if he can guess correctly the color of card many times, then it probably proves that okay, he has some power at least. Okay. So what they then some person is asked to conduct the test. So this person sits in front of that supposedly psychic person and holds the cards and asks him to guess. Now what happens is, he guesses every card incorrectly, all 25 cards. He guesses each and every card incorrectly. As a result, these FBI people feel that oh, you are right. They call this mathematician and tell him, you are right, he couldn't guess even a single card correctly. So it means he really doesn't, I mean, he failed very miserably and he doesn't seem to have any psychic abilities. But this mathematician actually gets, annoyed. He says, no, 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 don't dismiss him so fast. He says that ideally, when you are asking someone to guess a card randomly, there is a 50% chance that the card would be guessed correctly, because there are only two possibilities, red card or a black card. So there is a 50% chance of correct guess even randomly. So if the person is guessing randomly, still he would be able to get 50% correctly. Now you are saying that he has got all 25 cards wrong, which means he did have some knowledge, because chances of getting all 25 cards wrong when guessing randomly are actually same as chances of getting all 25 cards correct. Okay, because the binomial distribution, we will see the graph in a minute, the binomial distribution is symmetric. So probability of 0 success is same as probability of 25 successes. So it means that it is very, very unexpected, because chances of happening this is very low, means this is very unexpected that with random guessing he will be incorrect in all cases. So it basically means that he is screwing with us. He knows the cards, he can actually predict the card correctly, but because he doesn't like that we are testing him, he is purposefully giving us the opposite answer. Okay, so even though it seems like a worst failure, it is actually an indicative of great success. Okay, so that's why we need to remember this. So so we discussed this. Bernoulli distribution is used when you have binary data, 0-1 type of data, success, failure, working, non-working, etc. And then we went for binomial. So now I'll show you the graph of binomial. See, what do you have to see in this graph? Here I have taken the size parameter of binomial as 10. So you can have at most 10 values, and success probabilities are changing here. Can you see the cursor? Can you see hand moving here? Hello? Can you see this hand cursor?
Yes, ma'am.
Okay. So success probabilities are written over here. So right now this is graph of probability equal to 0.1. So when success probability is very low, then number of successes will also be very low. Okay. So 0 successes have high chance, 1 success has high chance, and 10 successes has very low chance, almost 0 probability. Okay. Now I will start the animation, so the graph will start changing and with the change in this probability. So keep an eye on this probability and see how the graph changes. Okay, the probabilities go from 0.1, 0.2, etc. Right now this graph is positively skewed. We have seen skewness, right? So you have peak towards left and a long tail towards right. So right now this graph is positively skewed. Let us see how it changes. Okay, so now for 0.9 the graph is almost opposite, it is negatively skewed. For 0.5 the graph is symmetric. Okay, so binomial PMF is symmetric if success probability is 0.5. It is positively skewed if success probability is less than 0.5, because if the chances of success are less than 50%, then the number of successes will generally be less. So you will have peak on the left side. Whereas if the chances of success are more than 50%, then number of successes would be towards higher side, so you will have peak towards right. Okay, so this is binomial distribution. Then this is one example of binomial distribution. It is known that the discs produced by a certain company will be defective with probability 0.01 independently of each other, and the company sells the discs in packages of 10, okay, and offers a money back guarantee that at most one of the 10 discs is defective. So they say that if you have 2 discs defective in your package, then you can return the package and you will get your money back. Okay, So now they want to estimate what proportion of packages is returned. See, this is a very valid question, because when you want to have something like warranty fund kept aside, okay, or when you want to keep some money aside for replacement of such defective products, etc., you need to have an estimate of how much money is required. So you need to have an estimate of how many packages will be defective. So here in every pack there are 10 discs out of, and probability of each disc being defective is 0.01. Okay, so what is the guarantee that at most one of the 10 discs is defective? So at most one means either 0 discs are defective or 1 disc is defective. So what we will do is we will compute reverse. So because we want what proportion of packages is returned, so we want to see how many packages have more than one defective. Okay, more than one defective. So if X is the number of defectives, then at most there can be 10 defectives in a package, and probability of each disk being defective is 0.01. So X follows binomial with 10 and 0.01, and probability of X being greater than 1, that I will compute as 1 minus probability of X being 0 and probability of X being 1. And these two probabilities we can compute as by using this. So 10 choose 0, p raised to 0, p is 0.01. So 0.01 raised to 0, 1 minus 0.01 raised to 10 minus 0. That would give me probability of 0 defectives. Similarly, I will get probability of 1 defective. 10 choose 1, 0.01 raised to 1, and 0.99 raised to 10 minus 1, that is 9. Okay, so this is how binomial distribution is used. Here is another example. A communication system consists of n components, each of which will independently function with probability p. The total system will be able to operate effectively if at least one half of its components function. We have to check for what values of p a 5 component system is more likely to operate effectively than a 3 component system. So so what we say, system will be able to operate if at least one half of its component function. So for a 5 component system, if 3 components are working, or if 4 components are working, or if all 5 are working, then the system works. Okay, so 3, 4, 5. So we add these probabilities. Probability of 3 components working, probability of 4 components working, and probability of 5 components working. Okay, for a 3 component system, it would work if at least one half means either 2 components work or 3 components work. So 2 components work and 3 components work. So we have to compare these probabilities. So these probabilities, so 5 component system is going to operate effectively means this would be larger than this if p is greater than or equal to 0.5. So this is another example of binomial distribution. Okay, then if I mentioned, if we increase n, that is the upper bound in binomial, and if we decrease success probability, then we get Poisson distribution. Okay, so here we have two curves, two graphs, one is red and one is black, and as n increases, see how the graphs start looking more or less like each other. So we are increasing n here on x axis. See, for n equal to 100, the graphs are more or less the same. Okay, and success probability is taken to be very small. So this is how binomial and Poisson match. So this we saw as Poisson PMF, e raised to minus lambda, lambda raised to x upon x factorial, where lambda is the mean number of mean count. And now I will show you the graph of Poisson PMF. So here lambda is 0.1. We will change values of lambda and see how graph changes. See, as the mean increases, probability of higher counts increases. Okay, so when mean is 2, then you have many, I mean, you have chances of getting 3, 4, 5 also as counts. Okay, and here is an example of Poisson distribution. Suppose that the average number of accidents occurring weekly on a particular stretch of highway equals 3, then calculate the probability that there is at least one accident this week. Okay, so on an average there are 3 accidents every week, so we have to compute probability that there is at least one accident this week. So x is number of accidents per week on that stretch, then x follows Poisson with 3 as lambda. Why 3? Because it is given that average is 3 and we want probability of at least one accident. So at least one means one or more. So probability of x being greater than or equal to 1. So this ideally we have to compute then probability of x equal to 1, x equal to 2, x equal to 3, 4, 5. We have to add all of them. So that becomes difficult. So we compute this as probability of 1 minus probability of x equal to 0. Because greater than or equal to 1 means it should not be 0. So complementary event. So 1 minus, when I put x equal to 0 in that formula for Poisson PMF, e raised to minus lambda is the only term that remains. Okay. So 1 minus e raised to minus. Here is another example. If the average number of claims handled daily by an insurance company is 5, what proportion of days have less than 3 claims? And what is the probability that there will be 4 claims in exactly 3 of the next 5 days? Okay, so this type of questions can also be answered using Poisson. So in fact you can take this example as homework, okay, and try to solve this. I will also try to share few more examples which you can try as homework. And in many of the statistical distributions, generally if you change certain parameters, for example in Poisson, if you increase lambda, then it converges to normal distribution. So here this red curve is normal and the bars represent Poisson probabilities. So here lambda is equal to 10. Let us see what happens when I increase lambda. See, for lambda equal to 100, the two graphs are matching, like they are almost matching. Okay, so as lambda increases, then Poisson distribution can actually be approximated by normal distribution, and that happens with many other probability distributions, that with certain changes in parameters we can approximate those distribution by normal distribution. And there is another thing called as central limit theorem, which says that if you have large samples, then generally that sample mean tends to behave like normal distribution. Sampling distribution of the sample mean becomes more or less like a normal distribution. So that's why normal distribution is important, but we will start that in the next lecture. I had assumed that you have had discrete distributions already, so I was going to start with normal, but since you didn't seem to know, so we discussed some discrete distributions today. In the next lecture we'll start with the normal distribution. Is it okay? Let me stop then. Thank you.